So here is the second fundamental theorem of calculus, and it actually establishes a very important relationship between differentiation and integration. It says if f is continuous on an open interval containing some constant a, then for every x in the interval, the derivative of the definite integral of my function from a to x is equal to f of x. So this is suggesting if you do the derivative of the definite integral of a function going from a to x, you essentially get that function back out, but in terms of x, not in terms of t. And we can actually see this based upon what we've just been doing so far with the first fundamental theorem of calculus. You could think for a second, let's evaluate this definite integral in a theoretical sense. The antiderivative of little f would be capital F of t. And so if you have capital F of t and you're evaluating that at x and then at a, and ultimately we're going to take the derivative of this, you can see that you'd be doing the derivative of, let me erase that, you'd be doing the derivative of capital F of x minus capital F of a. But what is the derivative of capital F of x? That's lowercase f of x. A was a constant, so what's the derivative of a constant evaluated into the original function? Well, that would just be 0. So again, you can see that we established this inverse relationship between differentiation and integration here. So when you get questions like number 9, when you see the derivative of a definite integral of a function going from 1 to x, you could simply say, oh, well, I know that in a sense the differentiation and the definite integration from the constant to x kind of cancel each other out in a sense. I don't get just 1 over 1 plus t to the fourth because I know everything is going to be in terms of x now. And so my answer here is just 1 over 1 plus x to the fourth. So there's really no work. But there's a lot of variations that you might see to the second fundamental theorem, things like example 10. And can you see in example 10, we have the definite integral of secant of t going from -1, and this is to a function of x. So it's not as simple as doing what we did before where we said, oh, well, if we're taking the derivative, oh, and I notice that I'm actually missing the derivative notation there. So if I'm doing the derivative with respect to x of this function, or of this definite integral going from -1 to a function of x, it is not as simple as simply saying, oh, it's the secant of x or something like that. But we can kind of go back to what we just did up here and figure out what you would do. So if I have the integral going from a constant to some function of x, the antiderivative of little f of t would be big F of t, and then I would evaluate at my upper limit and subtract what I get when I plug in my lower limit. And so this would lead me to doing the derivative of capital F of g of x minus capital F of g, or no, I'm sorry, minus, so it'd be capital F of g of x minus capital F of a. Get rid of that. Again, though, capital F of a is a constant, and the derivative of a constant is 0. What's the derivative of capital F of g of x? This is actually a composite function, and we've done this before. This is chain rule. So the derivative of this would be the derivative of the outer layer evaluated at the inner layer, and then you would multiply by the derivative of the inner layer. So this is saying, for a question like example 10, if we're doing the derivative of the definite integral going from a constant to a function of x, we can see that we are going to take that function of x and substitute it into the f of t function, and then we're also going to multiply by the derivative of that upper limit. So the shortcut here is you essentially end up plugging in the x squared here. So we do get secant of x squared, but it doesn't end there. We also have to multiply by the derivative of that upper limit. And so the answer to example 10 would be 2x times the secant of x squared? This is kind of a tricky question, and honestly, I'm more focused on the basic idea that differentiation and definite integration going from a constant to a function of x are inverse operations of each other, and so I'm more interested in what you're seeing in example 9, but you're going to see examples like 10, maybe just a couple in this class, but you're going to see weird integrals like this moving forward, and so it's good to kind of try to generalize this simple second fundamental theorem to something a little bit more complicated like what we just did down here. Okay, one last idea in these notes, and this is something that we actually covered in the very beginning video a little bit. Remember in the beginning video when we did the definite integral of velocity, and we did that from a to b, and I ended up showing you that that was equal to the position at b minus the position at A. That was a net effect or a displacement that we were looking at. And so this speaks to the fact that when we do definite integration, we're finding net areas, but when those functions actually mean something, we're finding the net change in the function. So the definite integral of a velocity function from A to B is the net change in the position from A to B. So again, the definite integral of velocity from A to B is the net change in position from A to B, or the displacement. Now, if I were to do the integral of the absolute value of velocity, this is where you would never have any negative velocities. And so if you think back to the very first video where we did have a negative velocity, if we're doing absolute value, then that would be above the x-axis. So what this would end up doing is it would end up adding in all areas, and so this is going to find a total area. And if you're finding a total area in a context like this, it's not displacement that you'd be looking at, but this would lead you to total distance traveled. So you should try to be familiar with this notion of doing a definite integral now has meaning. It's the net area, but it's the net change in many times a velocity function, and the net change in the definite integral of a velocity function is the net change in position, or the definite integral of the absolute value of velocity is the net. You don't want to say net change anymore because everything's above the x-axis, so that's where we say total distance traveled. So if you ever do a definite integral of a function, it's the net area. If you ever do the definite integral of the absolute value of that function, it's the total area. Okay, hopefully I didn't confuse you too much there, but this net change theorem is something that is also going to be important as we apply calculus moving forward. Okay, I'll do one more video, and in that last video, we will take a look at just a few practice problems.